Okay, good morning, everyone. Hopefully you can hear me. Um, so last class, we were talking about sort of things that impact glycosylation, and we were still really focusing on this one strategy, these glycosyl bromides, and just using that as the platform to explore that. So I'm going to talk a bit more about different glycosylation strategies today, a little bit protecting groups. I think this will carry through to next class as well. Again, I haven't received any email requests for the handbook of chemical glycosylation. But if you need more reading on that, please let me know. Otherwise, you can also look up all of these terms on Wikipedia. They're all out there. Like, this isn't super obscure stuff. So we're going to walk through a bunch of different strategies, and then we're going to start compare and contrast, figure out why you might want to use one over another for given applications. So the first one we're going to start with is glycosyl sulfides, sulfones, and sulfoxides. And they're all related. So what are these? Well, they are this. Where R is anything. So it's I just need to minimize my music, move this over. There we go. I have all the right windows in the right places. So just want to make sure I am, I got all organized this morning. When this morning I am going to have all the slides ready to go, subtitled, everything, and then I got a bit distracted because, of course, I did. Okay, let's start talking about that stuff. There we go. So this is a sulfide. We can oxidize it up to a sulfoxide. Or a sulfone. This is just a sulfoxide. We're going to oxidize that further to a sulfone. Theoretically, you can reduce them. I'm not actually aware of anyone doing that. I think because it's often incompatible with the protecting group strategy you have on the sugars, and normally you wouldn't want to reduce from. We'll see why. It just wouldn't really make a lot of sense. It's not particularly useful. So as you go up this way, reactivity increases. So this is really useful because let's say you have, minimize that, okay. Let's say you have complex series of reactions. Maybe a sulfone or a sulfoxide wouldn't survive those reactions, but a sulfide would. So you can sort of carry along as a sulfide, and then when you're ready to do something with this anomeric position, do glycosylations, you can turn it into a sulfoxide or a sulfone. So it acts as a way to mask and protect that anomeric center and prevent it from reacting until you're ready for it to react. So how do you get these things to react? Well, I think the pattern we're going to follow is we'll follow how to make these, all these different things, then how to use them, and where relevant, how to interconvert them, and then sort of special things that happen with these different types of acting groups at the anomeric position, and how you can exploit that to get what you want. So your synthesis of these, in almost every case, you are going to make the sulfide. You don't make the sulfoxide and sulfone from anything but the sulfide. So you make the sulfide, then you oxidize it up. Just gives you better control. So after we finish with the sulfur ones, we're going to switch and have a little divergence about protecting groups because they've shown up, but we haven't really discussed anything about them. We just said, hey, they're there. We've got these different types of participating groups. So one that's really easy to get is a sugar with all acetates. We would call this a peracetylated sugar. Per being universal. And I guess because I haven't drawn any special stereochemistry on there, it's glucose. I have noted that it's a beta glucose though. So I might use BF3 etherate. We're going to use dichloromethane, and we're going to use thiophenol as a nucleophile. Okay, so because it's glucose, we know that the C2 position there is axial by definition. So this is our promoter. This is our glycosyl donor. This is our glycosyl acceptor. We are using a non-participating solvent. If you remember the solvents, dichloromethane doesn't do anything. It's not like acetonitrile or ether. It just does nothing. It does not interfere with the reaction. So do I expect an alpha or a beta product from this reaction?
Beta.
Sorry, Ronaz, you're really quiet. That might be on my
Beta.
Beta. Great.
Yeah.
Why?
Because of the anomeric effect and because of the OHC that we have and can participate, in the reaction and helps that our nucleophilic be in a beta position.
Perfect. So just make sure that we're pronouncing it right. So it's the ankymeric effect. The anomeric is the one that gives you alpha?
Ankymeric.
You might have said that. I might just not have heard you. So I'm just making sure everyone else is on page. So Ronaz is absolutely 100% correct. You will get the beta product because of ankymeric assistance. Okay, so if we break that down and go, what's the mechanism of this? I'm an organic chemist. I love mechanisms. So we're going to get an activation. Let's draw this baby out. With BF3. BF3 is very oxophilic. It's a Lewis acid. If you want to go back to your definitions of acids and bases, loves binding to oxygen. Might as well have added H+. It's just H+ does all sorts of other things, whereas BF3 binds to oxygen. It's much more specific. So makes this bond, we get this. This then has to undergo the ring flip to the right twist chair such that the acetate group is anti-periplanar to the lone pair of the oxygen. If you don't know what I'm talking about, go back for 2 lectures and rewatch that lecture. And you will go to the oxocarbenium intermediate. And as I was saying, when we were talking about the bromides, I was saying it doesn't matter how you get to the oxocarbenium. Once you're at the oxocarbenium, the rules take over. So the rules here are we have a non-participating solvent, but more importantly, we have a C2 acetate, and the C2 acetate is going to win. I can't think of a single example where you have a participating group at C2 and you don't get the trans product, like the beta product, unless it's mannose, in which case you get the alpha. Again, as we talked about last class. So that's going to participate. We are going to get so that looks a little bit like this. You could draw that double bond equally between either of the oxygens, the resonance structures of each other. And then this forces the thiophenol to come in and attack and give us the beta product, regenerating that C2 acetate. So this is a good way to make beta thiophenols. And this is very, very typical. This is probably actually the easiest way to put them on. I'd say 95 to 98% of all anomeric thiophenols come from peracetylated sugars, go to the beta thiophenol. But occasionally somebody just wants to be different, because different gets you papers published. So let's say you had the beta bromide or the alpha bromide. Let's say you treated that with sodium, ammonium, tetramethylammonium bromide. And we saw when we were talking about the bromide stuff that will give you the beta bromide because it goes to the more stable, because everything's equatorial. You could then crystallize that, and then you can treat that with sodium thiophenol and THF. Now, we're under basic conditions here. Almost all glycosylations we see are done under acidic conditions. The previous one was done with BF3. The other ones we've seen are all been done with silver salts. Those are all acidic. And here we're under basic conditions. And so the oxocarbenium formation is going to be slow, but you have a really strong nucleophile. So you can do an SN2-like displacement of the bromide with thiophenol. In this case, you're going to get the alpha thiophenol. I think there are so few alpha thiophenol, and again, we have a C2 acetate, but it doesn't matter because we never made an oxocarbenium this way. So we never got a chance to use anchiomeric resistance because there was no oxocarbenium. I think there's a half dozen examples of this being done in the literature. It's kind of pointless. I don't know why anyone would do it because you just make the beta thiophenol and you go from there. But it's doable. If you really, 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 really want to do it, you can do it. Similarly, you can go from the alpha bromide, do the same chemistry, you'll get the beta thiophenol. Again, SN2-like conditions. But sometimes this stuff can be just a little bit too harsh. So as an alternative, notice the wiggly line. If you go back to lecture 1, we were talking about the immunorotation. You can't have a stable one compound if you have an OH at the anomeric position. It'll flip back and forth between the equatorial and the axial. It would love to be able to make furanoses too. It can't because there are acetates at all the other positions. We use thiourea. Water potassium carbonate. In this case, I use methyl bromide, and I end up with that. So this is also much gentler. So we in one reaction up there we used BF3 which is a very harsh Lewis acid. In the second one we used a sodium salt, which is a very strong base. In this one we use very, very gentle conditions. Thiourea is about as gentle as you can get. And then base, and then a weak, like just an alkylating agent. I'm trying to think if I want to go through the mechanism for this. Nah, probably should. I'm going to test on it. We could. So this, you have to, like the key idea here is that this is in equilibrium with the aldehyde as the absolute key thing that you need to remember. Otherwise, this doesn't make any sense. You can't turn alcohols into sulfurs just by treating them with thiourea. That doesn't do anything. But if you remember that this is the aldehyde, and thiourea has a major resonance structure with a negative charge on sulfur. And what we're relying on here is there is a lot of thiourea. And thiourea is a weak, that carbon-sulfur bond is weak. A carbon-oxygen double bond in urea is probably one of the, along with carbon dioxide, is probably one of the most stable carbon-oxygen forms there are. It's like urea is a lot like carbon dioxide, actually, if you look at it, right? Carbon dioxide is carbon double bonded to oxygens. Urea is carbon double bonded to one oxygen and making two bonds to nitrogen. And that's because it wants to make two single bonds to nitrogen, not one double bond to nitrogen. But urea is basically the equivalent of carbon dioxide. They're kind of the carbon fixing molecules. And it's why when we try and make, using the Haber process, we try and make urea, is because it's a very easy way to get nitrogen out of the atmosphere, is turn into something else that's super stable, and urea is super stable. So anyways, you'll get that. Then this is weird, and because sulfur is a second row element, it can adopt angles that normal healthy elements don't want to adopt. So if we do that, we make a four-membered ring, which as a carbon chemist makes me very uncomfortable. But it's not silicon, that's sulfur, just some extra magic line around. So we have this four-membered ring. That's just then going to collapse through a retro 2+2 to give double bond sulfur and urea. And again, the driving force here is super stable. So we really, really, really want to make urea. And we just did. And there's, there's still the acetates in here. Then this guy just ring closes onto the urea. And note that that you're going to get an S minus. And the negative charges, because they need to be solvated, prefer to sit equatorial. You also have a really shitty anomeric effect from a negative charge because it's already negatively charged. It doesn't want more electrons, so it's not going to benefit from an alpha anomeric effect. And then your 1,3 dipolar, 1,3 diaxial interactions with the other axial groups here are really, really bad because you have a freaking negative charge. You have a huge electron cloud around you. It wants all the space in the world, especially when you're solving in your big atom. You can't get an S- axial to save your life. So this just reacts with, the methyl iodide that you add in the final step, or the methyl bromide. I use bromide, so I'll use bromide here. Doesn't matter, of course, you can use either. And you get your final product. So what we're relying on here with this formation is this very, very gentle reaction where the urea is interacting with an aldehyde. You can stick it with almost anything else in there, and the urea is just going to stare at it and do nothing. So it's just a very careful choice of conditions. The water and the potassium carbonate assist with making sure with the ring closing here and a few of the other steps, because they just make sure this is taking place under base catalysis. I have an O- drawn there, for example, and I wouldn't have an O- if it was neutral. It'd be an OH and kind of sit there and might not do anything. Okay. So we've got three ways to make these glycosyl sulfides. We can make them from anomeric bromides to an SN2. We can make them from anomeric acetates through acid catalysis using BF3 etherate. We can make them from the free reducing sugar. This is called, sorry, I use that. I didn't realize it's the first time I've used that terminology. This is a free reducing. This is a stupid name. It should be a free reducible sugar. And the idea is that that anomeric OH, that OH that isn't attached to anything, can be turned into an aldehyde, and you can reduce aldehydes. So it's a reducible sugar. But for whatever quirk of reality, we've inverted the meaning of the words, and we call it now a free reducing sugar. I don't understand why, because you're reducing the sugar, the sugar's not doing reducing. Again, don't make the rules. So you'll see this terminology show up with sugar stuff quite often, especially with oligosaccharides or polysaccharides, like multiple sugar chains all attached to each other. And it normally, the free reducing sugar is the one on the far end that has a free OH. Everything else isn't free reducing because it doesn't have a free OH because it's using it to attach to something. Okay. So, okay, let's say we have our thioether ether. What can we do with it? So let's say we've got it. Doesn't really matter what the R group is. Thiophenol is very common. The reason thiophenol is very common is it doesn't stink too badly, and it's relatively easy to work with. Most thiols are foul, like just unbelievably foul. One of our labs was basically unenterable for a while because we had a thiol in a fridge inside a double container, like it was in a container, like its own glass bottle, inside a Ziploc bag, inside another container. And obviously a drip had gotten out somewhere in the first container and it just stank up everything. So thiols are foul. Thiophenol is less foul than most of them. It also crystallizes nicely once you stick onto a sugar. The sugar behaves nicely. The phenyl group can be seen by UV. So it's got a few advantages, and that's why we see it. But there's no reason you can't use an ethyl or a methyl. You don't want to spell thiomethane. Methane thiol is pretty nasty too. Just we are designed as human beings to hate this smell. So it doesn't matter what that is. So you can use anything. But let's say we're using that. What we need to do is we need to get a double activation because it's actually really hard to get that to react. It doesn't really want to do a lot of things. So we're going to use two things. We're going to use NIS, I'll say what that is in a moment, and TFOH. And I'll say what that is in a moment, and I'm going to say, and by a moment I mean right now. NIS is N-iodosuccinimide. TFOH is triflic acid. So triflic acid is probably, it's the strongest normal acid. You know, people claim they're always making stronger acids, but those acids are weird. Triflic acid is a normal acid. It's got a hydrogen attached to something. Normal. It's like minus 13, if I remember right. The pK is ridiculous. It's just a stupid strong acid. And NIS, if you haven't seen it before, I really hope that this nitrogen iodine bond is making you a little bit upset. I hate when I see heteroatom bonds. It's because they're inherently unstable, and this one is no exception. It's an inherently unstable heteroatom bond. But what's really important to note here is you can treat this molecule pure with triflic acid and nothing happens. Like the molecule will fall apart before it does anything in a controlled manner, which is pretty cool because triflic acid is so strong, and we've created, you know, a thioacetal. Like acetals fall apart with a little bit of acid and water, but you put this in triflic acid and it's reasonably stable. So you need to add the NIS, and you use just a catalytic amount of triflic acid. And what it's going to do is actually activate the NIS. So let's see how that happens. So rule of thumb in chemistry, if there's a catalyst, it probably does something in the first step. Otherwise, everything would just stare at each other, or things would react immediately when you need a catalyst. So catalysts are normally involved in the first step. We have a catalyst. It is an acid. It's a source of H+. You protonate something. Let's protonate an oxygen. What does that do? Well, now I've got a decent resonance structure. Okay, main M+. The nitrogen would love some electrons. It could grab those electrons from a nitrogen iodine bond, but then we'd have an I+. And that's weird. So let's not have an I+. Let's let sulfur take care of that problem for us. So we've just created a sulfur iodine bond. It's a bit weird. That bond is actually quite reasonably strong. It's quite reasonably favorable. So again, I'm going to do the lie. Remember what I'm saying here is flip to the half chair, open the half chair, make the oxocarbenium. I'm shortcutting it with 2 arrows because I don't want to have to draw a whole bunch of half chairs. But that is what's happening. You have to always kind of keep that in the back of your mind. Oh, look, we made an oxocarbenium. This now just does oxocarbenium chemistry. So everything we've discussed, solvent effects, nature of the protecting groups, nature of the temperature, blah, 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 takes over and defines the chemistry. In this case, we have a C2 participating group, so we expect to get beta products. So if we have the same molecule, now we'll change it a bit. But another way to activate these, so we're going to put a benzyl group on there. And let's say we had an anomeric bromide. Sorry. Another way to activate this, besides using NIS, is bromine and a silver salt. Now notice I need the silver salt. Bromine itself isn't going to react, which is saying something, because bromine reacts with everything. But these thioethers are pretty stable. They just don't do a lot of stuff. And so you need to add help. And so what happens here, notice it's basically the same thing we just did. It's just a different way of making a positively charged halide. Silver triflate completely dissociates. So we get this. It obviously took up more slides than I thought I would. That's probably good. I have a tendency to crowd slides too much. So we can make, and I'm aware of that, and I'm trying to be better. So we can make something like this. Now we're basically back where we were with the iodine, except we have bromine, iodine, bromine, same diff. Oxocarbenium. Now in this case here, we have no C2 antiomeric effect. So we're going to think the anomeric effect is going to drive that and whatever the glycosylation is, and we can affect that with our choice of solvent, with what solvent we did this in. But again, we have a second way to activate these thiophenols. Okay. Couple more things I want to briefly discuss. These are probably the two primary ways, because we're going to going directly to the oxocarbenium for reaction, but sometimes you might want an alternative, because maybe you're using a thioether not so much as an activating group, not so much, so an activating group is something you use to, that's what we've been doing, but more as a protecting group. And you can see I'm going to talk about protecting groups. So maybe what you want to do is deprotect it, you want to recover something else. So if you have that, and you treat that with bromine and lots of heat, we can go back to the glycosyl bromide. Theoretically, I've never actually had this work, and because you have to choose the right solvent and it precipitates out, and it depends on what sugar it is, but theoretically, on paper, this works. Somebody's got it to work. I don't know if I trust them. So another thing is we can interconvert between one type of activating group and another type of activating group. So if we go from using that to using NBS, H+, and water, well, we just saw what happens when we use NIS and H+. Let's stick with NIS. We saw what happened when we use NIS and nitric acid, normally at low temperatures. If we use H+, we add a bunch of water, you'll go to an oxocarbenium, and then you'll go to an OH. That can be useful because there are a couple of groups that come nicely from an OH. I'm just going to leave this here. We'll come back to this probably next lecture, the lecture after. We'll go to trichloroacid imidates from there. When we generate nodes from OHs soon enough. The other thing you can switch between is you can go to a fluoride. Again, what we're kind of doing in most of these cases is we're going through that oxocarbenium. It's just we're stopping with something. So let's say we have NBS and a reagent called DAST. I'm going to show what DAST is. We're going to come back to this. We discussed fluorides briefly. I was going to not discuss fluorides, and I went, shit, I think I need to. This is DAST. That just looks weird. Sulfur with 3 fluorines and a nitrogen on it. It goes back and forwards between being available and not being available based on how explosive people think it is in a given year. Can't remember if it's available right now. But it blows up because it's got a lot of fluorines attached to a heteroatom. And, you know, fires and explosions are driven by oxygen because it's a really strong oxidizing agent. And oxygen's got nothing on fluorine. Fluorine is a really strong oxidizing agent. If you're ever bored, there's actually, no, you don't even need to be that bored. This one's actually kind of interesting. There's a book written about the history of the isolation of F2, like fluorine gas. And it's basically a story of people dying. Everyone dies. Because it's really toxic and it's explosive. And like people are losing limbs, and people who don't die lose limbs. And the people who don't lose limbs lose like all the hair on their faces and become poisoned and die young. So it's actually not a fun, very fun story. But fluorine is really dangerous. And chemists are idiots. And I think those two go together. They used to be. We're better at safety now. And we also, why would you want to isolate fluorine? Like that just, no. Don't do it. Never say yes to that. So we can get anomeric fluorides. And this will be mostly off because of the anomeric effect. So we've got a few ways to activate it. We've got a few ways to treat it. I just want to make one other note here. Here I used NIS or triflic acid. You could have, there's a few options here. It's kind of irrelevant whether you use NIS or NBS. NBS is the same thing with bromine instead of iodine. And if you don't like triflic acid, you can use TMS triflate. TMS triflate is a lot like triflic acid. If you don't know what that is, silicon with 3 methyl groups attached to the triflate. So basically, instead of an H plus, we have a silicon plus. You can think of this as fancy H plus. Basically the same thing, except you don't need to have any water present. It could be completely dry. It's hard to get completely dry H plus. It's very easy to get completely dry TMS plus. And so it's a good source of an equivalent kind of agent. So we have a few different options on how we can activate it. We've got a few different options on how we can treat it to convert it to something else that we can use. But if we want to do some chemistry, what we really want to do is we want to convert it in the presence of a nucleophile. And so the nucleophile I want to use here is, this is going to be our first example of a glycosylation with a glycosyl group. So far we've been using methanol, ethanol, isopropanol, whatever. Because I'm going to want to divert into discussion on protecting groups. Okay, notice my favorite conditions during this are NIS and TMS triflate. 0 degrees, dichloromethane. Okay. So we've got two different thioethers. One on each of those molecules. One's got benzyl protecting groups. One has benzoyl protecting groups. If I remember right, we're going to go over this, but benzyl is that. So CH2 phenyl, benzoyl, very similar, but the CH2 is now a carbonyl, and so benzoyls are esters. They're like acetates, they're C2 participating. So benzoyls are C2 participating versions of benzyls. And I'll try and be very careful to pronounce the difference between ill and oil, and I hope everybody can hear that. I'll be as careful as I can. Because with a Canadian accent, benzoyl becomes benzyl very easily. So I have to channel my inner Englishman. So we treat those together and we get only a single product. You know, assuming we don't use way too many equivalents of so just gonna say one equivalent of everything. If I use more than one equivalent of NIS, I will react with both thioethers, but I'll get selectivity if I only use one. So that goes an 87% yield, which is pretty damn good. I'm lying a bit here. They're not using NIS in the 87% yield. It's a little bit lower with NIS. They use a special equivalent reagent that it would just be reagents for the sake of reagents, and we have enough reagents. So we'll stick with this. So what's going on here? Why don't we react with both thioethers? Mechanistically, hopefully you can draw it now. Sulfur, the NIS is activated by TMS triflate. TMS adds the carbonyl, the NIS, creates an I+. The I+ reacts with the sulfur. You get an oxocarbenium. The oxocarbenium is then attacked by the OH. Sorry, it's alpha. Oh God, I have to redraw it. I can't in good conscience show you what I just did there. That's disgusting. It was an abomination, that bond angle. No, that doesn't make any sense. You get an oxocarbenium. The oxocarbenium then reacts alpha because of the anomeric effect, because there's, some non-participating solvent, dichloromethane. I will write DCM. I should always write CH2Cl2, but old habits die hard. I will write DCM. So DCM doesn't participate. There's no C2 anchiomeric effect. There's no driving solvent effect, so we are going to favor alpha. But that doesn't explain why the left-hand thioether reacts and the right-hand thioether doesn't react. Okay, now we're going to stick with this title. So why does the left hand react and not the right hand one? Let's come back to that question. So we have protecting groups. What is a protecting group? We've been talking about them, but what the hell are they? I think we discussed this in class number 1, but let's just revisit it.
It's an inactive group.
An inactive group? Is that what you said? Because you guys were answering at the same time, which is great. I love that. But Hazel?
Just it's an inactive group. Inactive group that's supposed to well, it should be an inactive group that can be got rid of later on.
So let's just say inactive group. Let's say a group let's say something that inactivates a functional group. It should also be in and of itself inactive, but we're trying to inactivate a functional group. So I like our circular use of the word group. We're going to use. Okay, let's switch to a thing that inactivates or passivates. A functionality. And I agree with your second part of your definition, Hazel. That can later be removed. To restore functionality. Absolutely. Yeah, that's a good working definition of a protecting group. So we need them in sugar chemistry a lot, because when you think about what your average sugar is, this is galactose, my favorite sugar. Like it's 5 hydroxyl groups in a ring, right? Those are all OHs. They all react in a similar way. We're going to see in this protecting group discussion that there are some differences that are general. So of these OHs, which one do you think under neutral conditions is the most reactive? To an electrophile, a standard electrophile. Like, let's say I had just a standard electrophile, and you have lots of time, like all the time in the universe, because the reaction is going to be slow with no base or Lewis acids or anything. But just which of these OHs is the most reactive towards that?
The one that is in this C1 carbon.
So Ronaz is saying the one carbon one. I'm going to say under basic conditions, that one wins, but under neutral conditions, it doesn't.
I'm thinking
So
the axial.
I am going to
ones,
point out that most reactive under basic conditions. Because you're not wrong. Just I did specify neutral. Sorry, Hazel, you were saying?
No, I was just thinking it's probably not the anomeric one. So maybe wait, is that 4? The axial one.
Okay. 4 is actually not very reactive. So let's step back a second. So Rona has identified 1 because the electronics on 1 are different. It's got this like weird anomeric effect, donation, instability of the OA of the charges and things because of everything we've discussed. It's weird. Is there anything weird about the electronics of any of the other 4 hydroxyl groups, or are they all basically the same electronically?
You want to say that because they're all OH, so there's no difference between them?
Yeah, electronically they're all about the same. So, but reactivity is always a complex interplay between electronics and sterics. So sterically, are they the same?
Ethyl one. It's the least hindered, no?
Which one?
It is. The ethyl one, 5.
5?
Well, by 6.
6?
Yeah.
Yeah, this one's primary, right? Least hindered. Most reactive. Okay. Cool. So those two really stand out. The anomeric and the C6 one, you can normally get a lot of really selective chemistry going on because they are generally the most reactive. On galactose, so every sugar is different, and I'm sorry for this. On galactose, this one is number 3 because adjacent to an axial. How does that help? Well, it's equatorial. Equatorial is less hindered than axial. Like by definition, right? I guess not by definition, but if we think about, we don't want things axial when we have a chair because of the 1,3 diaxial interactions because of the hindrance. So axial substituents are less reactive than equatorial substituents. And an equatorial substituent adjacent to an axial substituent actually has more room than an equatorial substituent adjacent to other equatorial substituents. So being equatorial and adjacent to an axial is good. Which makes this guy number 4 because he is also equatorial. And this guy is number 5 because he's axial. That being said, that is a true. Everything I've written there is a true statement. But it's statistics. Good freaking luck differentiating between 3, 4, and 5. Like numbers 3, 4, and 5. They're so close. Yeah, there's a difference. And if we're debating angels on the head of the pin, we can say that this is definitely true. If you ran a million molecules, 500,000 would go on 3 first, 300,000 would go on 4 first, 200,000 would go on 5 first. But that 5 to 3 to 2 is not a great selectivity. So not as useful, and so it's not synthetically all that useful. You don't want to rely on it. So although we can have differential reactivity here, because they react different, you don't want to rely on that differential reactivity. It's not very good. So that's why we need protecting groups, because we need to mask a lot of these OHs, keep the OH we want available, let it do its chemistry, and then remove the protecting groups on the other OHs. And we saw that in the last example, where this guy over here, I didn't really highlight it or anything, but if you'll notice, the C3 position here is an OH, and everything else is protected. And so that allows that OH to react. Nothing else can react because there's no other OHs. And then later on, we will be able to remove all the protecting groups. Okay, so that's why protecting groups are important, because we need to stop all the OHs reacting, because that's just going to be a freaking mess. And we need to ensure that the right one we want reacts. Okay, so I think in general, if we're thinking about protecting groups, we've got a series of them. Well, there are really 4 main tools that we can use to protect and deprotect. We can use acid, sensitive. So we take these off with acid. We can use base sensitive. We take these off with base. We can use hydrogen sensitive. And then there's kind of other, light, heat, nucleophiles, oxidation. We're not going to talk a lot about the other. I'm going to leave those off. If you want, you can look into that. You're welcome to use them on any assignment question. You can use anything, right? So you can go into literature and dig stuff up. Just if you use something a little weird, just always leave the citation in your answer. But these main 3 are our main strategies, and probably account for like 90% of all protecting groups out there, or use of all protecting groups. They're probably like 10% of all protecting groups, but lots of people use things as a protecting group. They use it once, it never gets used again by anybody else in the history of mankind. So under the acid sensitive ones, our main one are silicon based. So things like TMS, TES, TIPS, TBS. We'll go over what these are. I'm actually just going to rearrange. I'm going to put TIPS underneath. It's not, I have to get this right. Dimethyl DMPS, dimethylphenyl. So So we'll come back to those. And then we also have, you know what, actually those are specialty. I'm gonna keep those to the side. Okay. Under base sensitive, we have the acetates, the benzoyls, pivolates. Under hydrogenation, really benzyl. Well, benzoyl is also hydrogen sensitive. Okay. So what we can do with the silicon ones, for example, is I had this series. So they come off in different orders. So TMS, TMS chloride is this. These are, I'm going to draw the chlorides of all these. You don't actually use the chlorides. Some of these use the triflates, but it doesn't matter. Trimethyl silyl chloride. Use this, and the way you put this on, the way you put all of these silicon ones on. Say you had this handy thiophenol that we were just talking about. Everything else is an OH. Take imidazole, normally dichloromethane. We stick TMSs on everything. Okay. Those same conditions work for everything else. So what's happening there is the initial reactions with the alcohol and the TMS chloride. You generate a protonated species where the OH is still present. Imidazole then comes in and removes that proton, giving you the OTMS. If that's right, and then you do the other alcohols. Imidazole is a weak base. It cannot create an O minus. That's why we use it. We don't want any O minuses. We don't want some crazy reactivity. We want nice, gentle reactivity here. So the OH reacts with TMS chloride to generate OTMS at one equivalent of HCl. And the HCl is mopped up by the imidazole. So we can do this with all these. So TES is very similar. It's triethyl silo. Okay. The next one I had on there was DMPS. Dimethylphenolsilane. I've used this so rarely in my life that I had to take a moment to think about what the abbreviation was. Then we have TBS. This also gets called TBDMS. They get used interchangeably. They are the same thing. But TBS is an abbreviation of an abbreviation because we like 3-letter abbreviations. And TBDMS is a little lengthy. What that stands for is tert-butyl dimethyl silane. And all of these are the chlorides. DMPS stands for dimethylphenolsilane. And then we've got TIPS, which is just a great acronym, and that's triisopropyl silane. So what's happening here, as we're going down from TMS chloride to TIPS chloride, we're increasing the sterics. Steric bulk around silicon is getting larger and larger and larger and larger. And so what we have here is a trade-off. The smaller the steric bulk, the easier it is to put on, the weaker the acid you need to use to remove it. The larger the steric bulk, the harder it is to put on because it's sterically more bulky, and the stronger the acid you need to remove it. And so you can actually play with this because TIPS is so big that you can actually mess with it. So if we have a sugar that we were just working with there, we treat this with TIPS chloride, one equivalent, imidazole, and dichloromethane. So conditions we just had 0 degrees. We only have one TIPS chloride, so we would need 4 TIPS chlorides to put one on each of the OHs. And we only got one. Which one's it going on? I gain some caffeine while you think about which one it goes on, because I desperately need caffeine. I'm falling asleep.
That is more accessible. The one that is more accessible.
Absolutely. That always wins. I was up really late last night writing reference letters for medical schools. So I'm feeling it. Yeah, you're going to put it on there and you're not going to touch anything else. Now, do you think you would get the same selectivity if you did this with one equivalent of TMS chloride? It's a lot smaller.
I forgot SARS TMS was bigger.
Nope, TMS is smaller. TIPS is the biggest.
I'm sorry.
So TMS is the smallest.
Oh, was the smallest, so it can, protect it as much as possible.
Well, if we only have one equivalent,
Indeed.
is it going to be very selective?
Oh.
TIPS goes C6. It's not going anywhere else. The TMS, is that going to go C6 only?
You said just one equivalent.
Yeah.
So TMS small enough to go on C1 as well?
Well, we have C1 protected with the thiophenol, but we have C2, 3, and 4 open.
C3.
Yeah, it's going to go everywhere.
Yeah.
And this comes down to the fact that the TIPS chloride is very, very big. The C6 hydroxyl is very accessible. So very accessible, very big, that works. The other OHs are not very accessible because they're all secondaries. It's harder for the TIPS to go on those. It's actually really hard to put TIPS on all of the positions of a sugar. It's impossible. It's very, very difficult. Whereas the TMS chloride is very small, so it can go anywhere. It doesn't care. It will go on C6, it'll go on C4, it'll go on C3. It doesn't care that C6 is all that accessible because it's so small that it doesn't differentiate between the sites. Everybody else is somewhere in the middle. In general, not generals. TIPS chloride and TBS chloride are selected for least hindered alcohols. They're also the hardest to take off. TMS gets used very rarely as a protecting group for sugars because it comes off so easily that if you look at your sugar wrong, your TMS group pops off. So generally what gets used a lot is TES. If you want to put a silicon group on every single hydroxyl group that's available, use TES. If you want to put it selectively on only the most accessible OHs, use TIPS or TBS. If you want something that's going to like go on in a reaction, come off in the same reaction, like a step down, TMS gets used a lot there. But and no one will use the DMPS that I drew. This gets used very rarely, but theoretically it's available to you. Its main benefit is that it's fluorescent, so it's nice to find on TLC plates and things. But these guys are very, very selective. So how do we take them off? Well, let's say you put all your TESs on. We can treat this with like HCl and water. And that will take them off. You should look up the mechanism. Your water and acid. But with TIPS, it's really, really hard. The problem with it is that it's so hindered that the water acid thing doesn't work very well. Like the acidity required to take it off is normally so strong that the rest of your molecule is going to start falling apart. So what we tend to use with this is we tend to use tetrabutyl ammonium fluoride, which, as you can clearly see, is not an acid. Yeah, it's got a positively charged nitrogen in solvent. I don't know. Let's do it in THF. Doesn't really matter. It's got a positively charged nitrogen and a negatively charged fluorine, but it's not doing this by acid. How it's doing this is F minus loves silicon so much. Like it's one of the strongest bonds out there is a fluorine silicon bond. And I guess because oxygen silicon bonds are really, really strong, and fluorine is like 1 over and just makes an even stronger bond. I don't really understand what makes bonds strong and weak, like single covalent bonds. The patterns are there, but they aren't always intuitive. Anyway, so what happens is fluorine attacks silicon. Now, generally, when we draw something like this, I would draw an SN2. If this was a carbon, this would be incorrect. I would need to draw a second arrow because I'm about to make 5 bonds to silicon. Silicon's fine with that because it's a third row element. It's not a second row element. It can make 5 bonds, and so that's what it's going to do. And of course, it's going to break something, break a bond. It's not going to break a silicon-carbon bond because that would generate a C minus, and that's really unstable. It could go back and break the silicon-fluorine bond, but as I said, that's a really, really strong bond. We've just formed it. The only bond that's left to break is the silicon-oxygen bond, and that's what it does. And then, you add a bit of water or something, you scoop that up and make it all neutral and stuff. So that's how we put the silicon on. We put it on with imidazole. We take it off with acid or fluorine. The last thing I'm going to talk about today, because we're not getting through other protection groups, let alone all the other glycosylation techniques, because that was an absolutely insane timeline, which was never going to work, is I want to look at how we can use silicon to do something a little bit different. Let's say I have a slightly different reagent here. I'm going to add 2 equivalents of this. And then, I don't know, 4 equivalents of imidazole. It's going to be a little bit more than that in reality. Dichloromethane, 0 degrees Celsius. So it's kind of like TIPS, except this has only got 2 isopropyl groups, and it's got 2 chlorides. What do you think where does this react first? This isn't a trick question. Very similar to the previous question. It's going to react at C6 first. Again, really hindered. Lots of isopropyls. Big. Kicks out a chlorine. Again, even there, I drew it as an SN2. It's not. The OH forms a bond first. You make a silicon with 5 bonds, and the chlorine leaves. It's just, I just don't want to draw an intermediate. It's hard to see this over here, but we have a silicon, 2 isopropyl groups, a bond to a chlorine. We have another one of these left. So what do you think the next step is?
Still, I cannot let go of C3.
Sorry?
I cannot let go of C3, the OH, which is
Okay, you want to react at C3. Let's think of, so yeah, so see, I agree that I'm going to put you off a step. I'm going to say, yes, it's going to happen, but not right first, because that's going to involve an OH finding another molecule of that. Is there something that can happen faster?
Form a
You see
5-member
too.
ring.
I heard a ring.
To form a 5-member ring.
Right. One, but I think it's 6. 1, 2, 3, 4, 5, 6.
Oh, yes, 6. I keep forgetting there's another carbon there.
Yeah, it's really easy to do. I do too, to be fair, Hazel. We're going to be looking at 5 and 6 membered rings next class with set 9s. Now, if you're getting I'll accept drawing it anyways, but you can actually easily draw a chair over here. And then you can really feel fancy that, hey, I drew a 3-dimensional chair with another chair and all my chairs are interlocking, and isn't that awesome? So what we've just done there is we've closed the ring. That's pretty cool. So we protected C4, which is the least reactive hydroxyl group in the entire thing. We protected it second because of its location relative to C6. It was sitting there just waiting to grab onto the silicon, because C4's reactivity isn't because the oxygen is short of electrons or anything. It's unfortunately it's the axial, and so it's hard to get to. But when this big dangling electrophile is sitting right next to it, it just snaps shut. Now Ronaz can't let go of C3, and I'll give it to her. I'm actually not 100% sure whether this goes on 2 or 3 first. 3 is more available under normal circumstances, but now we have a big bulky thing over here, which is right next to 3, and we don't have that next to 2. So I think 2 might become more reactive at this point. I'm not willing to put money on it. So how about we go with 3, because it doesn't matter. So we're going to do the same thing with the other equivalent. There, I was trying to draw a 7-membered ring, Hazel, for no particular reason.
Sorry, what?
I was trying to draw a 7-membered ring there for a moment for no particular reason. So it's very easy to forget how big your rings are. So I'm gonna give in to Ronaz's C3 hydroxyl fetish, and we'll attach it there. And that then opens up the ability for us to do exactly the same thing, except with the C2 hydroxyl. So if I had only used one equivalent, I would have only protected C4 and C6. Since I used 2 equivalents, I protected all 4 of them, but as 2 separate, really well-defined systems. And this is incredibly selective. The yield for this kind of stuff is normally in the mid-90s, which is great because you essentially did 4 different reactions, right? You had 4 different hydroxyl groups attached to silicon. There's lots of ways that theoretically could have gone, but this is about 93% yield. It's incredibly selective. And that battery warning both acts as a note that we have reached the end of the section, and that is 9:54, and we are at the end of the class. My battery lasts about an hour and a half, so this class is never going to go over very much. So next class, we're going to finish off talking a bit more about protecting groups, and then we're going to return to, I find it exciting, the relative excitement of glycosyl, sulfoxides, and sulfones, which are more reactive than the sulfides, which will allow us to do other stuff. And we're going to use that kind of as a platform to start discussing a few of how we can use protecting groups to try and manipulate these things. And then we'll see what more manipulations we can do with a few more complex activating groups. Okay, I think we're done for today. I am going to stop recording.